Welcome to all of you. In this lecture, we are going to discuss about symmetric FIR filter. In symmetric FIR filter, there are two cases. First one is the order is even and then symmetric FIR filter. Second case is order is odd and symmetric. In this lecture, we are going to discuss about the order is even and the symmetric. Let us first understand the concept of the symmetric FIR filter. Unit sample response of FIR filter is symmetric if and only if it satisfies the criteria of h of n is equal to h of m minus 1 minus n, where n is the sequence number and m is the order of the filter. So let us consider an example to understand this expression. Let us consider order m is equal to 6. An even criteria is being considered over here. And let us have the answer or the realization of the values something like this. So we are considering a predefined realization over here. Now if the order is 6, in the sense total there are values from 0 to 5, total 6 values, and they are going to have the h of n values represented like 2, 3, 4, 4, 3 and 2. Now let us apply this expression and verify, does it going to satisfy, does this is going to satisfy this criteria or not. Now at n is equal to 0, that is h of 0, that will be equal to h of 6. So m is having the value 6, therefore 6 is represented, minus 1, and then n value is equal to 0, so that is being written. Now if we simplify this, we are going to get h of 5. So that means h of 0 is equal to h of 5 is equal to 2. Make a cross check of that in this graph. So h of 0 is equal to h of 5 and its value is equal to 2. So the criteria is being satisfied. Similarly, if we substitute n is equal to 1, then it is going to say h of 1 is equal to h of 4 and its value is equal to 3, being satisfied. Then one more, at n is equal to 2, h of 2 is equal to h of 3 and its value is equal to 4. So in a simple term, we can say that with respect to midpoint, if we perform the folding operation, then the values which overlap on each other, so they must have the same h of n values. Then it is simply a symmetric FIR filter, and with respect to expression also, this is going to satisfy the criteria of the symmetric. Therefore this realization belongs to the symmetric FIR filter, or simply h of n is equal to h of m minus 1 minus n criteria is satisfied here. Now let us get into the realization of the case 1, that is the order is even and symmetric. Now the Fourier transform of unit impulse response is given by h of omega is equal to summation n is equal to 0 to m minus 1 h of n e to the power of minus j omega n. Let us call this as equation 1. Let us consider m be even. So that is what the criteria we are being considered, and for the sake of understanding, I am here considering the length of the m is equal to 8. So m is equal to 8 in the sense we are going to have the values from 0 up to 7, total 8 values. So with respect to position, if we represent in general, then this is going to be the position 0 and this value 4 is going to be the midpoint. Therefore we can generalize it as m divided by 2, and a value just before this midpoint is going to be m by 2 minus 1, and the last value is going to be m minus 1. Now we are going to make use of this generalized concept to take this realization further. Now this expression can be split into two parts. So first part is going to represent from starting till the midpoint, and then the second part is going to realize from the midpoint till the end. So splitting this expression, we are going to get h of omega is equal to n is equal to 0 to m by 2 minus 1 h of n e to the power of minus j omega n plus summation n is equal to m by 2 up to m minus 1 h of n e to the power of minus j omega n. Now this is what the expression we have got. Now for the sake of further simplification, we are going to make substitution in the second summation part. That means we are going to replace this n with m minus 1 minus n. So don't confuse the representation n present here with this n. You can just consider this as n updated or n new, and you can make a substitution to avoid the confusion. For the sake of simplicity, I just considered this as n. So that means only in the second summation, the n value is being replaced with m minus 1 minus n. So we are going to get h of omega is equal to, so this first summation part will remain as it is, that is n is equal to 0 to m by 2 minus 1 h of n e to the power of minus j omega n, plus in the second summation, after making this substitution, we are going to get n is equal to m by 2 minus 1 to 0 h of, see n is present here and this n is being replaced by m minus 1 minus n. So therefore this will become h of m minus 1 minus n e to the power of minus j omega, and in place of this n, m minus 1 minus n is being substituted. So we are considering a symmetric case. Symmetric case in the sense h of n is equal to h of m minus 1 minus n. Therefore, wherever this h of m minus 1 minus n is present, we can replace that by h of n. And this kind of expression is available in the second summation, where we can replace this complete by h of n. That is being done over here. So h of omega will be equal to, so this first summation part remains as it is. Second summation, so summation n is equal to 0 to m by 2 minus 1. So here you can observe, so 0 to m by 2 minus 1, so that has been just reversed, it is not going to affect. Therefore n is equal to 0 to m by 2 minus 1 h of n, in place of h of m minus 1 minus n, it has been replaced by h of n e to the power of minus j omega of m minus 1 minus n. Now in the next step, we are going to take this exponential into consideration, and we are going to divide this into two parts. So first summation retained as it is. In the second summation, n is equal to 0 to m by 2 minus 1 h of n e to the power of minus j omega m minus 1. So first part m minus 1 is being taken, that is taken as one exponential, into e to the power of j omega n. This n is the second exponential part. So minus is present here also, and one more minus present here. So these two, that will become plus. Therefore this exponential has become positive power. Now this is what the result we had got. So now in this expression, we can observe that some parts are common with respect to both of these summation. So that is, the summation range is also common, and the term h of n is common in both of these two. So we can take that as a common factor. So taking that as a common factor, we can write it as h of omega is equal to summation n is equal to 0 to m by 2 minus 1 is a common factor. H of n is a common factor. This part is a common factor. Remaining is the exponential part from both the parts. So e to the power of minus j omega n plus e to the power of minus j omega of m minus 1 into e to the power of j omega n. Now for this further simplification, we are going to make one substitution. That is, so a combination of these two is equal to 1. So that means e to the power of minus j omega of m minus 1 divided by 2 into e to the power of j omega of m minus 1 by 2 is equal to 1, because here is positive power, here is negative power, and if we multiply these two and simplify, then we are going to get the answer as 1. So that means it will become equivalent to multiplication by 1. So this substitution we are making it with respect to this first exponential. So in the next we can observe that h of omega will be equal to summation n is equal to 0 to m by 2 minus 1 into h of n. So this is a common factor into e to the power of minus j omega n. So taken as it is, and then it is multiplied with the value 1, and that 1 is taken as equivalent to this value. So why only this value means, if we make substitution of this, it will be helpful for us in the further simplification. That's why we considered only this representation. So this complete has been represented over here. Plus, in the second part, we can make an observation that e to the power of minus j omega into m minus 1, we can split it into two parts. So first part with m minus 1 divided by 2, second part also m minus 1 divided by 2. Combination of that is going to give us this answer. That is being done over here. So this single exponential has been split into two exponentials. That is e to the power of minus j omega into m minus 1 by 2 into e to the power of minus j omega of m minus 1 by 2. So if we combine these two, it is going to give this answer. So there is no variation into e to the power of j omega n. So this is written as it is. Now with respect to observation, we can say that there is one more common factor that we can take out. So that is this particular exponential. So it is present over here also, and also present in this part. So we can take one more as a common factor, and writing the expression, we get h of omega is equal to summation n is equal to 0 to m by 2 minus 1 h of n e to the power of minus j omega into m minus 1 by 2 taken as common factor. Writing the remaining exponentials, we get e to the power of minus j omega n into e to the power of j omega into m minus 1 divided by 2 plus e to the power of minus j omega into m minus 1 divided by 2 into e to the power of j omega n. Now this is what we had obtained. Now we are going to combine the exponential parts that are within the bracket. That means we are combining these two exponentials, and also we are combining these two exponentials, and writing the equation, we are going to get h of omega is equal to summation n is equal to 0 to m by 2 minus 1 h of n e to the power of minus j omega into m minus 1 divided by 2. So this is common factor multiplied with combining these two exponentials, we are going to get e to the power of j omega m minus 1 by 2 minus n, plus combining these two exponentials, we get e to the power of minus j omega into n minus 1 by 2 minus n we are going to get. So here it is minus and here it is plus. So a combination of this is going to give us minus. So if we expand this once again, I'm going to get back this expression. We have to take care of that. Further, if we look at these two expressions, it is in the form of e to the power of j theta plus e to the power of minus j theta by observation. And these two combinations is equivalent to the representation of 2 cos theta. So we can eliminate these two exponential, and equivalently we can realize this. In terms of 2 cos theta, where theta is going to represent this omega and further complete part. So substituting in place of these two exponentials with equivalent cosine representation, we get, so h of omega is equal to, so from summation up to this part, this is a common factor, into 2 cos omega of m minus 1 divided by 2 minus n. So in this expression 8, we can observe 2 is a constant value, we can take this outside the summation, and rearranging this complete expression, we can finally write it as h of omega is equal to 2. So this 2 has been taken outside the summation. So 2 summation n is equal to 0 to m by 2 minus 1 h of n as it is, and first written cosine part cos omega of m minus 1 by 2 minus n, then written this exponential part e to the power of minus j omega of m minus 1 by 2. So this is the final expression that we required. Further, h of omega is equal to magnitude of h of omega into exponential of phase h of omega. Now this is directly comparable with this expression where the magnitude part stands from this 2 up to this point and the phase stands with omega and onwards. So by comparing these two, we can write the magnitude as magnitude h of omega is equal to 2 into summation n is equal to 0 to m by 2 minus 1 h of n cos omega of m minus 1 by 2 minus n, and phase of h of omega will be equal to minus omega of m minus 1 by 2 if h of omega is greater than 0, and minus omega m minus 1 by 2 plus pi if h of omega is less than 0. This is what the final realization that is required. Thanks for joining.